Okay, so obviously, to those of you who have signed on, this is not the Karen Brewer you were looking for. Karen is a bit under the weather, and I've been asked to fill in. My name is Barbara Guerin. I'm the Quality Assurance Manager at HII here in Norfolk, Virginia. And Karen and I go back a long ways. In fact, we went to NDT school together. So that's where that relationship comes to play. We're pleased to have Jim Prindiville providing a 3-section presentation today. He will be discussing digital parallax RT, film versus DR, specifically the differences, and image processing. He'll provide an overview with one example. So with that, I will turn it over to Jim.
All right, I hope we're there. Does it look like we're there? Okay, well, I want to thank you all for participating in this webinar and thank Ghostrock and Karen and George and now Barbara for helping to support this. I always find these things a little bit difficult. I know some of you are at work trying to balance this, phone calls and meetings, and trying to do the best you can, and I certainly appreciate that. Others are at home doing the same thing. I'm obviously at home. Some of you might be in a hot tub. Others I know have just finished lunch and maybe looking for this as a sleep aid. But whatever your reason, I hope you're all able to get something out of it. So it was noted, this is going to be a 3-section presentation. The first is going to talk about digital parallax radiography, and the main crux of this is why not? It's easy to do. Then next, we are going to talk about really going from film to DR, since film parallax is the one we're used to, film parallax radiography. We're going from film to DR, so let's look at some of the differences. And then last, DR usually is incorporating some sort of image processing. I know last month, Ghostrock put on image processing, but it was really for CT. And CT generally doesn't require that much image processing. Things generally tend to be fairly flat, uniform. But for DR, there's a long list of things you can consider. And I'm just going to specifically, I'm going to mention a few and then specifically talk about one that may be a very common technique and can be a little bit complicated, but I just want you to realize the complexity of some of these routines. So with that, I will start with the presentation on parallax radiography. And traditionally, it's been with film. It's been used as an interpretation aid. In other words, you've already located a defect or whatever, and now you're trying to get some additional information, and the information it's going to provide is depth information. So parallax DR, we're going to be using the DDA, a flat panel detector, digital diode arrays. What makes it different? What advantages does it have over the older film techniques? And I'm going to present 2 different ways of acquiring the parallax. You can obviously, you'll use a lot more than that, but I'm going to present 2. So that's the crux of what I'm going to go through. So here's the basis from film. Parallax techniques are based on the principle that from 2 exposures made with 2 different positions of the X-ray tube, the depth of the discontinuity is computed from the shift of the shadow of the two indications of the discontinuity. And you can find good references to this in the ASNT Handbook, Volume 3, the new one that came out maybe a few months ago. The projected positions of the object closest to the source will shift the most. Therefore, you can determine how close an object is from the source by how much its image has shifted from one exposure to the next. So these are discussed in pages 445 to 453 of Volume 3. There's another similar technique, stereo, that also deals with a shift. Parallax actually measured the depth, where stereo gives you a visual depth perception. So here we have a little schematic that shows apart the X-ray source is a red dot on top. We have the film is on the bottom, and it's based on similar triangles. The triangle from the source to the indication is a similar triangle to the one from the indication to the detector. And traditionally, film has moved the source and has used sometimes a double exposure on the film. Now, stereo does a similar thing, but obviously, if it was film, you'd be using 2 sheets of film and have some sort of a stereo double viewer for the film. But we can deal with stereo images now with color monitors. If you use the red cyan glasses, or you have a stereo monitor with polarized glasses. And again, you're shifting the X-ray tube, maybe in this case, and then you're providing a stereo image to get depth perception. So to sum it, Parallax uses a tube shift and calculates the distance of the flaw from a given reference plane. Sometimes you can put top and bottom markers on the part, and you can kind of use those things as references. So that's kind of a summary, but it helps us simplify interpretation. So 2 issues that are complicating image interpretation are, you don't have the depth perception, and you really don't have any information on what the beam divergence is. It's not coming out straight unless your source is a long way away. So you've got a beam divergence. So if you look at the diagram on the left, if you look at the detector on the bottom and you see that red indication is, say, a crack, then you're going to assume the length of that crack is at your source to object distance, and you're going to measure it as going across here, and then you incorporate the magnification that you know, and you'll say that's the distance of your crack. Well, the crack may actually be going, so it's not parallel with your detector, in which case it is longer. But if you don't have depth information, you don't know that. So the question is, can we get a reasonable representation of the 3D positional information from indications in a part to simplify image interpretation for projection radiography? That's the question, and we hope that Parallax will do that. So why revisit Parallax today? Okay, we have digital detectors array, they're quick. You can get a second exposure, no problem. We also have computers with control. We control motion systems, whether that be a linear stage or a rotational stage. The computer can do the mathematics for you. You don't have to worry about that. You can also manipulate and enhance the images. So yeah, you can get nice, pretty images. But we can also present these on a graphical display. So those are the things we're going to look for that digital will do for us today. So again, I mentioned that we're going to have 2 different parallax techniques. One will incorporate a linear shift. The other one will be an angular rotation of the part. Since I was putting this stuff together during COVID, I didn't really have laboratory support for the linear shift, so it's a computer simulation. I did have some rotational data from laboratory stuff that was done, so I can use that to demonstrate the rotational, but this is pretty self-explanatory up here. So let's look at parallax techniques commonly move the X-ray source. So we're showing moving the X-ray source, but this may not be easy to do. Sometimes the sources are heavy, and get them, pointed in the right direction, doing that stuff may not be simple. And if you're dealing with a digital detector array and you're going to move your source, then you should take another gain field for your image, because now your beam profile has changed. So that means that with the DDA now, if I'm going to incorporate this technique, I got to take calibration files for the detector, the gain and the offset for the X-ray machine in one position, and then do it again when I shift the X-ray source and do it in the other position. That doesn't sound too good. Don't think I want to do that. But so all we really need is a relative shift. So instead of moving the X-ray source, we could move the part and the detector. The result's the same. It's a relative shift. But if we move the detector again, now we're going to have to get another calibration file and deal with another gain field. We don't want to do that. So don't move the detector. So you can move the detector by specifying a new 0 start position for the detector. Don't bother moving it. Just pretend it's a shorter detector and it starts a little bit further back. So then there's no need to take another gain field. So if we kind of demonstrate that, we have the part, we shift the part, and the red line was our start field here. And where the red line was over here as a 0 reference for this image, the 0 reference for this image is going to be here. In essence, we've made our detector shorter, but we don't have to do another calibration file. So there's no need for recalibration. So it makes it very quick then if you have a little motion stage to move your part. Or if you can't get a motion stage, you can't move your part, you could put the X-ray machine and detector on a C-arm, and there are some systems that are set up that way. So then just shift your C-arm. You're still going to deal with, some of this stuff for here, but it makes it very easy then to obtain a stereo image. So here I'm showing 2 stereo images. We have our indications coming down here for our first image, and then we're going to shift our part 2 inches. So we shifted it 2 inches to the left. So we got a new 0 start position here. So this part of our panel we're not using. We're calling this 0. And we can see coming down here, there's a slight shift over here. So then we're going to align those 2. Now, so we have the blue as the first image, the red is the second image. This is the part of our panel that is basically dead now because we eliminated our 0 start position. Now we've got a parallax image. We can basically shift these images and align on any plane from whatever distance from the X-ray source we want to. So if I just shift these planes a little bit, I can align it so that this indication lines up, and I happen to say I'm aligning it to come in at 30 inches from the source, where the source to detector distance initially started out as 60. And now I know that, oh yeah, so this is indeed 30 because this is where this indication is. Another comment while we're here, this presents a rather good stereo image if you want to put on a set of glasses. This one is going to be out towards the front of the screen. This one is going to be towards the back of the screen. You can tell by what side the red's on, what side's the blue's on. So what I want to do is I want to measure the distance between the blue and the red. Those are my 2 indications, one before the shift and one after the shift. So to measure the distance, well, let's just shift these things a known distance and keep track of what I shifted them so I don't have to drag my line clear across the screen. Let's just make them a little closer together and incorporate that image shift in my calculation. So I said, focus on a plane of 35. So that's why the 30 doesn't line up anymore, because I focus on a plane of 35. Now I can zoom in on this image to get a more accurate measure of the distance between the 2 indications. So now that I've done that, I should be having the computer calculate what the depth is. So at this point, I should have an estimate for the depth of the indications. And that depth right now is going to be the distance from the source. Where is it from the source? So I have other questions. Can I provide a depth Q overlays on the digital image? So for the digital image you're looking at, can I give you some sort of a depth Q on top of that image to let you know how close it is to the source or how close it is to the detector? And I think we're going to do that by putting circles around them and having large circles close to the source and close overlays to the detector as small ones. Then not only that, now I can calculate the beam spread so I can get a more accurate position for the X and Y position, because I will know then what the beam spread is, because as I mentioned, these things aren't coming out straight. So I know the X and Y position isn't truly where it shows on the X-ray detector. It's going to have that beam spread have to be incorporated. So now, can I provide positional reference for indications? Can we do like 3 orthogonal views, looking from the source side, looking from the top down, and looking from the side view? So can I give you a view of where the indications are, looking from the source side, as I show over here, looking from the top down view here and looking from the side view here. And then can we also give you at the same time the indications you called out? So that's the intent here. So here we are, we took our first two images, we shifted them, we measured the distances between the indications. So now we have an estimate of depth. Now we're looking at a depth Q overlay. So this is the image, which is our first image, image 1 here, first one. And we can see we have large circles here, which indicates this indication is close to the source. Smaller indications here are going to be further away from the source. Number 6, interestingly, should be back towards the source again. So now we have depth information overlaid on your initial image. Once we do that, we could calculate the actual distances between these things. So these indications are in sequence, number 1 up here, number 6 down here. So if I look at the depth or the distance between indication 1 and 3, it shows it's a little over 3 inches. And interestingly enough, if I look at the distance between indications number 5 and number 6, it's also a little over 3 inches. Well, you certainly wouldn't get that from your initial 2D projection. But this distance here, these are as far apart as these two are up here. And then we just happen to measure 2 to 6 and come up with about 4 inches. So we're getting some additional information which can aid in interpretation that we didn't have before. And it really was done by acquiring one more quick image by indexing the part, or if it's on a C-arm, the X-ray machine and the detector. So now we're going to look at seeing if we can display 3 orthogonal views. So we're going to just take our box, source side, top down, left side, and we're going to just fold it out so that the source side is going to be here, top down is going to be here with the source side here, detector in the back, and then left side is going to be over here. And we're going to be looking from the left side to the right, so the right's going to be further away. So here's our overlay. So now as we do that, there's no reason we just can't fold these out. So when we fold these out, we can look at this projection from the front. And these images here of where they are will take into account the beam spread. So they may not necessarily line up with what you see here. So it looks like over here, actually 5 and 6, according to, going in, let's call this the X direction, is actually probably a little shorter than what it is over here. But this would be a true X position. Then if we look from the top, we can see that this one, it's big, so it's towards the top. It's also towards the front, which agrees with this information because the circle is big, it's towards the front, it's up towards the top. And we can go right down the line and we can see 5, it's small, so it's towards the bottom, but it's also towards the back. So here we have 5 towards the bottom, and since it's small, it's obviously towards the back. And if we take a look at where 6 is, 6 here is basically towards the source, but it's small, so it's towards the bottom. And here, we don't know, we can see certainly here it's towards the bottom. And then we can come over here and get a third view, and look at this again. We can see 1's towards the front, 2, 3, 4, and 5 go further back, which agrees obviously with this. And then 6 bounces back up again towards the source. So, we have this layout now, which gives us the 3D information of where things are, again, with one extra exposure. In all truth, you only need 2 of these to get what you're really after, but the third one was thrown in. And then if you want to know what the indications look like when you flagged them, the indications are numbered up here, 1, 2, 3, 4, 5, and 6. That is what the indication looks like when you flagged it. So, there we are doing the parallax with the shift and providing you additional interpretation data. So again, I want to point out that from your initial, from here to here, is 3 inches. And from here to here is also 3 inches. And on the 2D projection, you're not going to get that. But if you look at it from up here, we're saying 5 to 6 is 3 inches. That makes sense. 5 to 6 can be 3 inches when you look at it, but certainly not from the one view. Okay, this is a similar thing. I'll go through this one quickly. This just listed 2 clusters up here. These clusters really look identical, except they're flipped and mirror images. But when I take a second image, there isn't much change in this cluster, but in this one there is. So the second image would certainly make you think that obviously these must be spread out in depth more than this one is. So when we do our measurements to measure the distance between the clusters, again, and you get the 3 orthogonal view. Here we are with the one that didn't change too much, and we can see that they really are clustered pretty well, except for 2 of them here, 13 and 19, which would be hard to get out of looking at this kind of a cluster. But you can see that these are kind of spread out, although most of them are here. They're towards the bottom. And then over here, we can see that, similar situation. Again, it's kind of repetitive in this regard, but you can see how they're laid out. And if we want to look at what indication we flagged, it's going to be the indication in the middle of these squares is the one that was flagged. And then they're identified over here. So again, it's just another example of showing a shift routine. So now let's move on to a different way of doing parallax. Let's use a rotational angular indexing. There's a lot of equipment out there, that is rotating something. There's a lot of CT stages that are doing rotation. There's a lot of rocket motors that are on long linear rotators, normally horizontally laid out. So there's a lot of applications that do rotate the objects. So, why not acquire parallax using a turntable and 2 different angular orientations? In this case, there's no need to translate the detector. There's no need to do an artificial shift of the detector. You can use the whole detector. We could say, well, the parallax calculation is more complicated, certainly, than it is for rotational. You don't just have similar triangles. This is much more complicated. Well, what do we care? The computer's going to do it. Just program the computer to do it. So here's what the calculations look like if you were to do that. If you're rotating something, then the computer can just handle that for you. You do need to know, similar like when you do CT, where the axis of rotation is and where the beam midline is. Those are things that are commonly acquired for CT and done with the calibration fixtures or whatever. So you do need to know those to reference and get started on this equation. So here's an example I have. This was done previously on some CT work from a part. So this was some of the CT work. It's basically a coffee can with PVC pipes and some miscellaneous things inside. But if we were to look at up here, we have a bent paper clip that comes out. And let's say we're interested in the end of the paper clip to the other end of the paper clip. And if we blow that up, we're really interested in how far is it from this end over to here. Now with the 2D, we could just measure this right here, but obviously that's going to depend on what angle we're looking at it from. If I look at it from 90 degrees, I'm going to measure this different distance. How do I know what it is? I want good alignment on this so I can get the correct alignment for it, or I can take a parallax shot and not worry about the alignment, or I can do both. So here's 0.90. And again, like I said, we have no depth information. The beam spread's we don't know what it is in there. We can get better estimates for X, Y, and Z positions. So let's start with 2 images. In this case, let's say 0.90. That's what we've got. And I'm going to flag these. Oops, sorry. 1 minute. And I'm going to flag these indications on the first image. 1, 2, 3, 7, and 8. This is 7. This is 8, are the 2 we're really interested in. And then I'm going to flag it on a second image. And again, they're in yellow right here. This is 7 and 8. And once I flagged them the second time, I already have my depth information. So I can see that 7 is closer to the source and 8 is quite a ways back because it is much smaller circle. And you can calculate it right here, what it is. In this case, instead of using X and Y, we're using a rho theta mapping. So we calculated the radius from the center of rotation and then the angle from a 0 reference position. So we have the rho theta positioning and the height of every indication now is computed once we indicate this second point. So here we are. And again, this is the reference I brought out before. You know, we really want to know what this distance really is without worrying about, you know, exactly what the projection is at. So if we just ask it to tell us what it is, it will draw a line. So we asked it to estimate the distance between 7 and 8. So it just estimates the distance between 7 and 8. And here, since I'm home, I took this crude measurement. This is a 5:1 scale. And I measured it here. And the measurements come out probably closer than you would expect, but that's what they were. All right, so let's take another example. This is a push pin. This is a plastic head, and this is kind of the steel pin. And I've got a distance from the point of the pin to the head of the pin, and I want to measure that distance. So I ask it to do a couple things. I want to take indication 1, indication 2. I want to show the results at an angle of 0 degrees, which I already did. It's over here. I can't read the results. They're hidden inside the image thing. I want to show the line. So there is a line drawn here. And I want to provide suggested alignment angles. So it's going to give me suggested alignment angles for 1 and 2. If I want maximum separation between the indications, in other words, I want to shoot down 90 degrees to the pin, then 10 degrees might be my angle. If I want minimum, or if I want to shoot down from the point to the head, then my angle should be about 2.79. So here I am at 10 degrees, and I should be shooting parallel or perpendicular to that pin head. And the pin measures 5.23 inches. But if I ask it that I want to shoot down the pin, well, here we are shooting from the head down the pin. So this would help if I'm looking to say, okay, I've got a crack and I want the orientation of the crack, and I want to shoot best sidelines between the front of the crack or the end of the crack to get my best orientation. So I can do that. Or if I want to say I want to shoot down that, then I can say, okay, I'm going to do the best I can to shoot down that. So that gives me my suggested positions. So now if I want to find angular indications at any angle, I can say, go to indication number 9, and I want you to go to angle 281, but rather than just show 9, show all the indications at angle 281. So it goes to 281, and then it automatically just flags then where these things are. So if you have indications and you're looking at a part and you've got multiple angles, but you think, is this the same indication as the one I had before? I'm not too sure. It appears to be. Well, if you had some sort of parallax information, you could say, show me all the indications I've flagged before at this angle, and it should be able to flag all those indications for you. So since I had number 9 flagged up here, I'm going to ask it to put it in some location. I want it centered on the detector side, centered on the source side. I want the source object distance to be on the right side. That means basically 90 degrees off that turntable. Want it to be on the left side, or I want it on the tangent position. The tangent position is different than this position if you've got a wide beam spread. So this takes into account the wide beam spread and puts it out on the tangent position. In this case, I said, take indication number 9, center it on the source side. So indication number 9 is this little void that's right here. And I told it to center it on the source side. So there it is, centered on the source side. Now we've got the similar review that we had before. This is our orthogonal views. Here's all our indications marked on the initial image. Here's the indications we marked: pinheads, 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 voids. This is the end of the paper clip straightened out. This is the other end of the paper clip. And then we mapped a rho theta mapping in this case, where this is the center of rotation, to give us our orthogonal views. So in summary, we're saying, can a DR inspector do more to simplify, his interpretation of an image? And I think with DR, it's simple to take a second image. I think with a lot of systems incorporating manipulators, that may be a linear stage or maybe a rotational stage, then we can go ahead and take a quick stereo shot, a parallax shot. And with those, we can, number one, estimate the depth. We can provide depth Q overlays on the DR images. We can calculate 3D positional estimates of where these things are. We can estimate the distance better than you probably can from just this standard projection radiograph, because you can get the alignment the way you want it, and you don't even have to show that alignment. You can predict the locations of any indications and any future angles you may want to require. You can align indications to one another at selected orientations if you have a turntable. We can provide 3 orthogonal views, and we can provide a montage of indications to assist. These are things you can do. I would think something like that might help make things a little bit simpler and easier for image interpretation. So with that pretty well summarizes what I have for the parallax radiography. And I think maybe, do we want to take questions before we go on to the next section? I don't know if we have anything yet.
Do you? Let's see if we have any questions at this time from any of the participants.
Okay.
Yeah, I was going to suggest if anybody online would like to ask a question, probably the easiest way would be to enter it in the chat. But if you would like to talk, just speak to us, we can raise your hand and we can allow you to do so if you'd like.
I do have a question here for you, George, or excuse me, for Jim. How do you see this being implemented?
Well, right now this is a script I wrote at Image J, so it's not something that's difficult to do. I would see it as part of a standard image processing package. The one thing that would have to be incorporated is an interface with whichever the motion stage is, if that's rotational or whatever. There'd have to be some interface there. But other than that, it's a standard kind of software type package that can be added on as just some sort of like with the rest of the image processing package. So it's not something that is truly that difficult. Like I noted, I did this in Image J during COVID in a couple of weeks. I thought, well, what can I do to play around with something? So
right.
So
we do have a question from Ed Goslin. He'd like to know if you'll make the script available as a plugin for Image J.
Right now, the script I have is not something that, I'm not a programmer. So it's not something that without considerable effort for me to clean it up necessarily is something that I would put out for general use. So, no, all the tools are in there. It's just a question of, grabbing the tools that presently exist and getting them into your script. So.
And where have you seen this in application, and who would benefit from this?
Well, personally, I have not seen it in application. That doesn't mean that, there isn't some people that have stumbled across this. I don't think a lot of it is necessarily novel. I personally like the 3 orthogonal views as something that might be a little creative, but I could see it like I do a lot of rocket motor stuff. And for the rocket motors, they're always concerned about how close voids are to certain things. Like how close is it to the ID is always a critical issue. And then sometimes they want to know how close things are to the tangent. And I see them struggling around taking umpteen images to try and move things out to the very tangent so that they can see how close it comes to the line, or keep moving it around to see how close it is to the ID, to the inner diameter. And that can be done simply with 2 quick views without necessarily knowing, without trying to struggle to put it in the right position. You could take your 2 views, calculate the X, Y, and Z positions, and then you can say, I want to confirm that. Let's use one of those automatic alignment things and say, I want to put it here, and have them put it there. So, I could certainly see it there. There's obviously piping inspections that go on, where they're concerned about whether is it in the insulator, whether it is in the near wall or the far wall, where is it within the pipe? Those things go on, so there's potential there. So, those are just 2 general examples.
So Farron Spalding commented that this was used on shuttle boosters and nozzle parts. So that's interesting to know. Hasina, I'm sorry, Bilyeu has a question and then a follow-on. I'll give you the initial question. They say, thank you, Jim. This is a great talk. They have a question about structures. Could the parallax technique be applied to measure cracks in bridges?
Well, bridges are difficult because you're remote. You're handling things, in a very difficult environment. And in that case, you're concerned about how far you move things. So, you're probably taking, in this case, maybe a C-arm type of a thing up there, but with a C-arm with some sort of a small indexer on it, so you can know that it's fixtured and it's moved a proper distance. So that's not to say those things can't be fixtured and made, but it does put you in a little more difficult situation because you need to keep those things aligned, and then you need to know how far you move it. So if you have a fixture and device that you can actually, get in position and it's light enough for you to manipulate and move that known distance, then yes, you could. But I'm not saying it's easy.
So their follow-up question is, in case one cannot get orthogonal views, would 0 and 75 degrees or 120 degrees work? Or are there preferable angles? Thanks.
Yeah, no, 0 and 10 degrees would work. 0, you pick your degrees. I just showed 0.90 because it was a common example for people to take shots at 0 and 90 degrees. But in some cases, actually shorter ones are easier because you need to identify where the defect is on the first shot and where it is on the second shot. And sometimes the less distance you move makes it easier to determine that you're flagging the right defects. So, in some cases, 90 degrees is not the way to go. Shorter is better. The one thing I will comment on rotation, however, is that things that are out towards the tangent on your rotation, when you move it on a projection image, it doesn't move as far when you rotate it. Where if it's towards the center of rotation and you move it on your projection, it's going to move a long way. So your measurements are more likely to be more accurate the closer the indication is to the center rotation on your projection image. And when it gets out towards the tangent, it's not going to move as far. That movement, when you rotate things around circularly, is sinusoidal. So things towards the center of rotation will move further, and things on the outside will move less on your projected image. So I will comment on that.
Good. Okay. I think with that, we'll move on to the next section, which is the differences in your discussion between film and DR.
Okay. Since we are moving from what is commonly a film technique to DR, we're going to talk a little bit about, some of the difference between film and DR, and we'll talk about contrast resolution and dynamic range. So right now, you pretty well talk about things. And today, film has high resolution. Digital detector arrays have low resolution. In fact, that's the reason everybody was always down on digital for a long time. They would say, oh, the low resolution, you're never going to get what you see on film. Yet for years and years and years, those that jumped into digital real early, like the location I was at was like in 1978, we were doing better than film right from the start. We did not accept the low resolution issue. And the reason is film has very low contrast to noise. DDAs have very high contrast to noise, orders of magnitude better than film. So let me point out the first situation, and I get most of this out of medical journals because they're the ones that produce it, but they're showing the spatial resolution here in this chart over here on the bottom left for film as the black line. And you can see this line stays real high as the spatial frequency or the detail we need to see gets tougher and tougher. And if we look at a flat panel detector, which is the yellow one here, we can see that, for the low big items, low frequency items, the large items were fine. But for the small item, resolution is really dropping. So is this the correct statement? Yeah, that's a correct statement. But so is this. We never measure contrast to noise on film. You just don't do it. But if we go over here, here's some examples been printed a lot from BAM. And it shows a weld and it shows the film they used, and they had to digitize this. So they used a very fine digitizer. And they show the signal and the noise because once we digitize it, we can do that. And we look at the detail we can see here with the cracks and things, and you'd say, oh, geez, look at these details, with this kind of resolution difference that this chart shows, we'll never see those with a flat panel detector. Entirely untrue. If you look at the flat panel detector, even with its low resolution here, look at the detail you can see here. Let's pick this crack out right here. That's not visible barely at all here, but it is here. You can go right down the line here and you can pull out the cracks and find detail that you see in the flat panel with its poor resolution that you can't see with film with its excellent resolution. And why is that? Why is that? It's because of the contrast to noise. The contrast to noise here is significantly better, and this is bad. And that makes all the difference in the world. If you read some of the latest medical journals, they're starting to say, we're starting to see that contrast to noise is extremely important, even more so than resolution. So, that's where we are with digital detectors. So yeah, resolution's not as good, contrast to noise is significantly better. So how does that relate? Now we have standards that we have to go with when we deal with digital detector arrays. And the standards call out, depending on how thick the part is, what the resolution is required to be for us to inspect it. So it goes down the line with different part thicknesses and says what your resolution has to be. So they also note that the contrast to noise is required to be a certain level. They generally specify the contrast to noise, and you can get these right from your system. Since we're doing digital, you go through a routine and it calculates the contrast to noise for you. You also go through a routine here where you put a gauge, a duplex wire gauge, where your part is, and you can find out your unsharpness. So those are standard routines now. And this is the duplex wire gauge. It leaves the specs for it that you're going to put on your part. But it also says, what diameter hole you're going to be allowed to inspect depending on what your contrast to noise is and what your spatial resolution is. So if the spatial resolution on the image is a certain value that you measured, and your contrast to noise that you measured is this, and they say you're going to substitute a value for what they call PT, which is perception threshold. You're going to substitute that value in here, and it will tell you, what diameter hole you're going to be able to inspect for. So those are things that you never did with film. Everything now is quantified. So you're going to go through these things to see if you can inspect. With film, it was kind of, can I see that penny hole? Yeah, I can see it. Okay, I can inspect. I tell you a number of times I wanted to have a standard plaque penny that only had 2 holes in it and have the operator tell me he saw that other hole. Because there was sometimes I certainly had my doubts. But now it's all calculations. So it takes some of that out. But to comment on this equation, it all relates to something called the Rose model. And the Rose model has been known for many years. And it says if you take the contrast and noise of your image and you multiply the square root of the area of the indication you want to see, then that gives you a value called perception threshold. And the higher that value is, the more likely it is you're going to be able to see that indication. So kind of the reference for that, if you use this equation, and if you come up with a perception value of 5, your odds of seeing that indication are 50-50. So you better be higher than that. So, the value that you want to put in here, I generally use the value of 10. This one here is a little bit different equation. And if you truly calculate PT, the value here comes out to be the square root of pi over 4, which is 8.86. It's just that they left that out of the equation to make it simpler. So their value 10 is really equivalent to a value of 8.86, which is about 9. So again, that's important to remember. If I want to be able to see something, the contrast to noise needs to be very high for small items. It doesn't need to be as high for large items because the square root of the area goes up. So that's a very significant point to remember. So let's talk about film response compared to a digital detector array. So here's a chart again from medical showing film response here. And we show our shoulder up here and the toes down here where we get these bends. The only place it's linear is from the blue line to the blue line. This is the only place it's linear. This is how much exposure was put on it. So only the exposure between here and here represents a linear part of that curve. So its dynamic range, how much it can cover radiation-wise, is pretty short. If we take a digital detector array, it's linear for a long way until it basically saturates. So it's linear throughout this whole span. So now its dynamic range is very large compared to film. So it says that if I want to cover a part that's got a thin section and a thick section, with film, I might have to double load that part if I want to cover that. Where with a digital detector array, I can cover the whole thing with just one exposure. So I don't have to take 2 exposures, or I don't have to double or triple a load of shots. I've worked on applications where they've triple loaded their film cassettes in order to cover the dynamic range they needed, where just one DDA shot would cover the whole thing. So with DDAs, better linearity, better dynamic range. Worse resolution, better contrast to noise. All right, but now we want to talk about something that's going to help prove the resolution on a digital detector array. So we all know that if we're taking a film shot, which shows up over here on the left side, and we've got a focal spot of a reasonable size over here, and we have a part down here in the black with an indication in the red, we've got film down here, and we want to take a film shot here, then commonly we're going to take a film shot so that we don't get a lot of source blurring. Because as you move away from the film towards the source, you're going to get source blurring from the size of your source. So we don't want that. So we're going to be close to the film. It was very common to just take your shots right up next to the film so you can keep that high resolution. Because if I move away, I'm going to start to fog it. It's going to start to blur. Now let's look at our digital detector. Our digital detector, our pixel size has got a certain size. It's not that small compared to grain size on film. So as you can see, it's rather large here. So if I take a shot right up next to the detector, then it's really going to show up as 1 pixel here. So it's pretty broad. But let's not do that. Let's take this, and here's our pixel size. Now, let's magnify our image and move it away. Well, what happens as we move it away? We're going to get more source blurring. So yeah, we're getting more source blurring. Here it is. It's across the white area here, say. That's our source blurring is right here, this triangle. So our source blurring's wide, but it's still only falling in 1 pixel. So it hasn't really changed. It's in 1 pixel here, it's in 1 pixel here. But what has changed? What's changed is the size, the relative size of my pixel at the image. So at the image, we have a magnification factor of say 2 now. So the effective pixel pitch at the image is half of what it used to be. So now my resolution has improved by a factor of 2. So the trade-off with digital detectors is to say, how much magnification can I put in by moving away from the detector until my source blurring gets to be too much that it overcomes what I'm gaining by the magnification. So there's the ASTM standard 2698, basically calls out the equations for calculating what they call total image unsharpness. And to do that, we know what geometric magnification is, source to detector distance divided by the source to object distance. And we're going to use what's called the geo unsharpness cubed plus 2 times the spatial resolution at the detector cubed, and then cube that, take the cube root of that. So it's the cube root of geo unsharp cubed plus 2 times the spatial resolution at the detector cubed. And then we're going to divide that by the magnification. So what is this equation doing? It's taking 2 times the spatial resolution of the detector, and it does that because you're not guaranteed your indication is going to fall just within 1 pixel. It may fall within 2 pixels. It might be on the edge. So that size, if you say I have a size of 200 microns, and that's going to be my resolution. Well, that defect that happens to be that size may actually overlap 2 of those and not necessarily just fall exactly inside that 1 pixel. The chances are better. There's going to be some not positioned exactly in there, but slop over to the one next to it. So in that case, you're going to do 2 times the resolution at the detector. And then you're going to calculate the source blurring. This is the blurring that we're looking at, this triangle blurring as things move out. This is the blurring. So I'm going to take the cube root of the blurring cube plus the resolution detector cube, divide it by the scaling. And that's going to be my total image unsharpness. So, this is what helps us out as we start to move away from the detector. This helps, this hurts. So if we look at a chart, so here we have a chart, we have a source detector distance of 60 inches, and we have a SRB of the detector, let's say 300 microns, and one at 200 microns and one at 100 microns. And if we plot that curve, and we say that our focal spot is 0.4 inches, we can say that for this, which is 100 microns, we're going to be better off closer to the detector because the detector has much higher resolution than this. And remember, we're multiplying this by 2. So we're comparing 0.4 to 0.2. Well, we're going to be closer to the detector here. So our SRB is going to be here like 45 for the best spot. But let's move up to where the SRB is 2. Now we got to multiply that by 2. So now this is 0.4 and this is 0.4. Well, where are we going to end up now? Your best resolution is going to be right in the middle. Those two equal. So our best resolution is going to be right in the middle at a magnification of 2x. Source to detector distance is 60. Source to object distance is 30. The magnification is 2, right in the middle. Now let's go up where the detector, 2 times the detector now is 0.3 times 2 is 0.6, which is worse than this. So we're going to be closer to the detector to get our best spot. So over here, we plotted what the magnification should be for your best spots. Now, do you have to be at your best spot? No, you don't. All you have to do is meet the requirements of your specification, whether that be ASTM specs that we quoted earlier or something different. You just have to be in that spot. You know, what restricts you from getting to the best spot? Well, it might be that your object is so large that if you move to a large magnification, you're going to not be able to cover your entire part on your detector, which means you're going to have to take more than one shot, which might not be a big deal. So there's other determinations on where you need to be. You certainly need to be wherever the specification says the minimum requirement is at. So again, this is the equations we were pulling out to plot those. Okay, again, we show it here. So if you did a different focal spot, this is a focal spot of 1, which is much larger than our 0.4. These are all the same. So everything tends now to push down to where the closer to the detector. Here's the total chart down here. I just blew it up over here. So when this gets really large, you get closer and closer to the detector. And that does it for that section. So I'm open to any questions anybody may have on that.
Okay. So we'll wait and see if any of the participants have any questions. So I'm going to go with one that's in front of me. And I'd like you to tell us how the contrast to noise ratio for CR compares with DR.
CR generally is accepted to be, you know, like maybe an order of magnitude or better than film. However, DR is significantly higher than CR. And the reason is with DR, you can take additional images. You know, you can average your images and you can do that numerous and numerous times. And the more you do that, the more you take out the random distribution that is the noise on an image, you know, that's the random flux, you know, coming from your source. So you can basically average that out and do much better than you can with CR. CR also has the disadvantage is that it also has grains in its imaging plates. And those grains also add noise to your image. But in essence, they're considered to be better than film. But, you know, DR is, again, a step above that. So.
Okay. And another question is, if DR has lower resolution than film, what if it can't meet ASTM specified resolution requirements?
You know, there's an interesting part in the ASTM standards that really takes advantage of the Rose model, which says to find an indication, it's the contrast to noise times the square root of the area. If the contrast to noise goes high enough, then you can basically reduce your resolution. You know, those charts in the picture of the weldments that we showed from BAM kind of highlights that point. And what it says that if you have to see a 2-2T hole on your image and you have to meet this resolution requirement, which you can't meet. If I can improve my quality level from the 2% 2-2T, if I can go to a 2-1T hole and see that, or if I can go to a 1-4T hole and see that, then I can reduce my resolution requirement by 1 wire. And the wire sizes are basically called out in their specs as to what that means. So it does allow you to take advantage of the increased contrast to noise that digital offers and allows you to say, If I can see a smaller hole than I'm supposed to be able to see, then I can reduce my resolution requirement this far. They call that the compensation principle. You're compensating for the lack of resolution. You're compensating for the fact that the contrast to noise is so much better. So that is in the specifications, and it does allow you to do that.
Very good. Okay. Alan Sanders would like to know which ASTM spec.
It depends. So 2698 is one you can certainly refer to. There's one that's the guide. There's one that's a guide for DR. There's one that practice for CR. I don't have that right off the top of my head. I know the one for resolution and duplex wire gauge is 2002. So that's the best I can do for that. If she wants to send me an email, I can definitely respond with the specification.
So any additional questions before we move on to the last session? Don't see anything. Okay, we're going to move on to image processing.
Okay.
An overview and an example.
All right, so yeah, we're on the last section here. So I appreciate everybody that would stayed with me. If anybody's been in the hot tub this long, it's time to get out. So, here we go. Let's review. So here's some of the things you might hear for digital, image processing options for digital radiography. This is just some of the common lists that are up there. There's the mean filter, the median filter. Last month, we heard how they used the median filter sometime in CT to reduce the noise. It certainly is a good one to use for that. Something called histogram equalization, local histogram equalization, contrast limited adaptive histogram equalization, sharpening filters, smoothing filters, Gaussian filters, unsharp masks, Wallace filters. We go down the list, Pruitt filters, Sobols, Laplacians, Mexican hat, bilateral filters. Then there's a whole thing that goes into fast Fourier transforms, wavelet transforms. It's almost endless, but there are some good literature out there. I'll quote a couple of them as we go through this. But some of the things that a lot of people find significant and somewhat easy might be an unsharp mask, a Wallace filter, bilateral filters. And then I'm going to go into one that's a little more complicated, but is a good filter. And I'm just using it as an example to show where some of these things are at. So they fall under the category of multi-resolution analysis. And I'm specifically going to talk about a Laplacian pyramid. There's also wavelet transforms and fast Fourier transforms that can be used to do similar things. But before I start, I want to say, well, why do we employ these things? Well, obviously, we want to make things look better. Well, what does it take for us to make things look better? And I think I want to start with looking at something of just, looking at our detector, our eye, and say, what does our eye need to make something look better so we can detect it? And on the chart is something you'll see from, vision books and medical or whatever. And it shows that we have something called photonic and scotopic vision. This is our daylight vision when things are bright. This is our vision when things are dark. Well, we're more concerned about photonic vision. And here's the light intensity. So when things are dark, we're down here in scotopic, night vision. And then as we move up here, we're moving into light vision. And the reason it's different is we have two different sensors in our eyes, rods and cones. One of them is good at night. Those are rods. Cones are good cones at night. Rods are good during the day. So here we're using our rods for the light vision. And the human eye can basically distinguish between, say, 800 or 1,000 grayscales. But it can't do that at one time. We have to adapt. And a good example of that, and one I used to see, is if you go into a dark theater and you're late. You're in a dark theater and it's late and you're trying to find a place to sit. And you look up from the bottom and you look up and you say, oh God, I can't see. I can see a few places. I don't know where. You don't want to sit on somebody's lap. So you're going to stand there for a few seconds until your eye adapts. Once your eye adapts, now you're able to see. So what is your eye doing? You know, your eye is adapting, like it says here, your adaptation level to a certain brightness. Now, once I'm in that brightness adaptation and I've adapted my eye, and I could have adapted anywhere along here, but once I've adapted here, then the limits of what I can see in the brights and the darks is really only about 50 or 60 grayscales. That's it at one adaptation. However, I could readapt down here and do it again, or I could readapt up here until finally it's too bright. Readapt up here. So I can cover that 800 to 1,000 grayscales, but not at one time. It's where does my eye adapt? So in digital radiography, we've got 16-bit detectors with 65,000 grayscales. And I can see 50 to 60 grayscales. So if I want to be able to see a difference, I've got to fit those differences in so they're within that kind of grayscale span without losing any information. And that's why I want to do some image processing. So the other reason I want to do image processing is contrast to noise makes a difference. So I can do one of two things there. I can increase the contrast or reduce the noise, or both. So with my image processing then, I'm looking at getting things into the right grayscale range that I need to see. I'm looking at improving the contrast and reducing the noise. Sometimes that's a several step process. So the more successful I am at doing that, the better I am at getting a higher perception threshold and being able to pull out what I need to see and having it fit inside that image. So those are the goals of image processing. Now I will comment that anytime you do image processing, you're going to lose something. You're going to gain something, you're going to lose something. I just hope that what I'm losing, and I better be sure what I'm losing, is something I don't care about. So let's move on to this multi-scale enhancement or multi-resolution analysis, something called a Laplacian pyramid. So basically, I'm going to take my image, and we'll say I start with a 2048 by 2048 images. And I'm going to do a couple things with that image. I'm going to scale it down. So I'm going to take that image at some point, reduce it down by a factor of 2 in each direction. And then I'm going to do it again, do it again, do it again, do it again. I'm going to scale it down. I could theoretically scale it down till it comes to a 1-by-1 image if I want. So over here, just to demonstrate that, I've taken a 512 by 512 image and I scaled it down to 128 by 128. Well, you can pretty much anticipate what happens when I do that. You know, here's my 512 by 512 image. Now I take it down to 128 by 128, and it's obviously a lot blurrier, a lot blockier. I'm going to lose fine detail when I do that, but that's okay. I'm not finished with this process. So that's one thing I'm going to do, but I'm going to do it in a certain sequence. I'm going to start with my 2048 by 2048. And before I scale it down to 1024, I'm going to filter it. And in this case, I'm going to filter it with something called a Gaussian filter. So what is a Gaussian filter? You know, if I have a 1 pixel point here and, you know, I have an intensity in there, it's going to show as a nice sharp spike. When I add a Gaussian filter to it, I'm going to blur that across a region, and the region's determined by the size of my filter or whatever. So I'm going to blur that point out. The amplitude's going to go down. This is going to be darker in the middle, but I'm going to spread that intensity out over a region. So I'm going to blur that image, and I'm going to blur it before I scale it down. Now, okay, so 24/8, run the Gaussian filter, scale it down. Now this looks stupid. I'm going to scale it back up. So I'm going to scale it back up. So it's the same size as this. Then I'm going to subtract these two images. And then I'm going to end up with something I'm going to call level 1. So I have a subtracted image. So what does that subtracted image look like? What have I done? I've taken really an image with a lot of sharp information in it. I blurred it, which means now I got a blurry image. I'm going to scale it down. It's going to get blurrier yet. And then I'm going to bring it back up, but I can't recover all that sharpness. It's going to be the same size as the original image, but it's going to be missing all the fine detail, all the cracks, all the edges, all those things are going to be gone. But I'm not throwing them out. I'm going to take this and subtract it from this. So now I'm going to end up with the sharp detail. That's it. I'm going to end up with just the sharp detail that's in that spatial range. Only things that are really fine lines. That's all I'm going to get. Now I'm going to repeat that again. So when I move it down again, I'm going to start getting fine detail that's not quite as fine as this level. So every time I move down a level, I've got very fine detail, not so fine detail, detail that's not as fine as 2, detail that's not as fine as level 3. So when it's really sharp, I'm going to say I have high spatial resolution. I can see cracks. When I have detail that's low spatial resolution, it's going to be voids. When I get down to the very bottom, if I go that far, I'm going to have just a grayscale, just the background grayscale. It's going to be the average intensity across that image. That's all I'm going to have. So each level I come down here is finer resolution. It's going to get to be higher frequencies as I go up, lower spatial frequencies as I go down. So now, if all I've done is taken those, eventually I'm going to add these all back together. So if all I've done is do that, and then I add them all back together, I'm going to get my initial image. I haven't done a single thing. I haven't thrown any data out. And if I just go through that process, do nothing else, and add it all together, I get my initial image. I don't want to do that. Well, let me back up just a second. Okay, I covered the lower spatial frequencies, higher spatial frequency components. All right, sometimes there's an example here, I'll point it out now. Sometimes they stop doing the reduction in size and they leave it alone and they come up with a funnel shape instead of a pyramid shape. Similar, but they just stop doing the reduction. But the rest of the process is the same. So I said if I add these together, I'm going to end up with the same image, but I'm not going to do that. I'm going to do a contrast enhancement on each one of these layers. And I've got a kind of a funny curve I can use for the contrast enhancement, but it depends on what parameter I put on that curve. So I can select what kind of contrast enhancement I'm going to do, and I'm going to apply that to every single one of these. So I'm going to change the contrast. I'm going to boost things that are in this kind of a contrast zone by quite a bit maybe, and not so much up at here where we already have high contrast. Then once I do that, I'm going to do two other things. The things that are cracks and high spatial resolution generally are higher to see, they're smaller area. So if they're smaller area and higher to see, I want high contrast. So now I'm going to boost the contrast, or I'm going to do edge enhancement. I'm going to reduce the contrast for things in the upper layers. So this is basically layer 0 at the top. And then as I move down. So if I move down to layer 2, which you might want to call layer 3, I start at 0. So as I move down, the contrast enhancement gets less. So for things that are small area, high spatial frequency, I'm going to boost them with high contrast. Again, that comes down to the Rose model. Now, I'm going to do the opposite at the lower end of the scale. At the lower end of the scale, so for layers 5 through 7 here, at the lower end of the scale, those are big items. So if those are big items, they're easy to see. I'm going to reduce the contrast for those things. So now I'm trying to fit things into the contrast range that I have here for my 60 gray values. by saying if it's a big item, I don't need high contrast. I can see that because the area is big. Give me low contrast there. For the items that are sharp, that are cracks and fine detail, the area is generally small. I need high contrast. So I'm adjusting to kind of the Rose model for these kind of things as I go through this. So here's an example of the same image I showed before. This is a magnesium cradle from a Corvette. So if I do that, here's the initial size. I'm reducing or scaling it down, and you can see how it gets smaller. I funneled this one so it didn't scale down any lower after a certain point, but these are definitely scaled down. Then I'm going to do contrast equalization. That's the first curve. I'm going to enhance the contrast on all these layers. So you can see how much these things have spiked up in contrast. Okay, now I'm going to do edge enhancement just on the top layers, just on the fine detail. Now I'm going to reduce the contrast on these lower ones because these are bigger items. And then when I'm done, these things all get scaled back up and added together. So when I scale them back up and add them together, this was my original image. This is the process image going through the Laplacian pyramid. And you can see the details here that you couldn't see before. You can see the details in here. Again, things that were here were outside my 60 gray value that I can see. And certainly the same thing for here, but now I'm fitting those within my limited range where I can see. And hopefully I'm doing that without eliminating some of the fine detail I need to see, or even some of the larger things with lower contrast that I need to see. So, that's what goes on with this kind of multi-resolution analysis. So there was one customer I had that had a generic package that was used for image processing for all kinds of things, not just radiography. And, that generic package, lead tools, certainly had this algorithm in it for image processing plus multiple others. And this was just their script for doing it. But you'll certainly find it in other packages as well. So that's what I have for that. And I'm willing to take any questions if anybody has any questions on that.
So I do have a comment from John Webster. He thanks you for the actual examples of the multi-scale enhancement images. One question we do have is your thoughts on what a level 3 should know about the image processing that they are using.
Yeah, that's easy. He should know that it works. But now comes the question, how does he know it works? I know the standard routine says that you put a penetrometer on your part and you take your picture, and if you can see the hole, you're good to go. I'd say the hole is generally representative of what would be a lower frequency item and not a crack. And a crack is a higher frequency item. So I would want to know some confidence that I can meet that higher frequency item. So where do I go with that? It was recommended by the Federal Working Group that representative quality indicators be used to show that you can see the type of indications you want to see in your part. So that's an item that is configured like your part that incorporates the type of defects you need to see. So you would have some sort of crack representative in there, some sort of voids and things that represent your penny, your minimum void size by some factor less than that. People recommend at least 2 times less than that or half that. Some say a third less than that. So you want to verify that you can see those. In essence, if you follow the spec as written by ASTM, however, it says that if I see the penny hole and I meet the resolution requirement, I'm good to go. Or if I meet the requirement from the compensation principle, I'm good to go. The concern I have with that is when you do this image processing, you're enhancing these spatial frequencies different, no matter which processing routine you use. So you might be enhancing the void or the penny hole and reducing the high frequency crack, and you don't know it. So I'd say, you need to make sure that you can see what you can see. So in each case, that might be something different as to how you answer that. So sorry, it's not a straight answer.
Okay, Michael Rodriguez says that was very interesting. Thank you. And George Hodges wants to know if you do this processing in ImageJ or some other software.
I do it in ImageJ. It's not a standard routine in ImageJ. It's not necessarily too difficult to write a script for it. So it is ImageJ. I do believe there's a lot of vendors out there that are employing this or something very similar. Most of them don't have a tendency to tell you. I know GE Rhythm years ago kind of advertised the funnel shape approach, which certainly appears to be awful close to what was presented. And I know vendors have what they call things, and when they ask, or even I ask, they always just tell me, Jim, you know what we're doing. And when I say you're doing this, they say, Jim, you know what we're doing. So I won't vendor without looking at their software and exactly how they lay it out to say for sure what they're doing. I certainly have my strong suspicions.
So you mentioned the funnel approach, but is anyone using the pyramid filter you reviewed?
Yes. It's my opinion is yes. And that's the best I'll tell you. You can ask them personally.
Okay. Do we have any other questions from, from Victor Marcancini says, Jim, an amazing talk as always. What effect would this level of DR processing have on a CT data set that would go into the radiographs prior to reconstruction?
Yeah, I would highly say do not do it. All your CT data sets go through a edge enhancement filter before they're processed. Those things are looking for a sharpened image. That's what they want. They don't want the image that we're trying to get. They want a sharpened image. So they have a couple different parameters when you go through your CT data set of different filters that you can use. There's a Shep Logan filter. There's a couple other type of filters. These are all sharpening filters to some degree. So, it's like running an unsharp mask. It's like running, a standard, 3x3 sharpening filter, except the parameters are a little bit different. So it wants a sharp image. It doesn't want what we want to look at for DR. So no, don't do it.
Okay, we'll see if anybody has any additional questions or comments. George, do you have anything you'd like to add?
No, not right now. I was just wanting to thank everybody for coming and thank Jim especially for joining us and give us an excellent presentation on 3 different topics. Is outstanding. So.
Okay, we have Farron Spalding would like to know what kind of target do you want to use for a GV signal with the 16-bit detector versus detection?
All right, I guess I don't. Can you read that one more time?
What kind of target do you want to use for a GV signal? Is that a good value signal? I'm not sure.
That's a gray value signal, yeah.
Gray value signal with a 16-bit detector versus detection.
There isn't specifically a target for a gray value. A gray value target, there is a target for contrast to noise. you certainly want to put enough flux on that panel. So the gray value is going to be the flux on the panel. So you certainly want to have that up to a reasonable level, but you don't want to saturate your image. So, you want to, ideally, you want to put as much flux on there as you can with making sure that you're not saturating your image. You want to cover your whole dynamic range. So there isn't a specific value. You have to stay so that nothing in your image that you need to see goes above your 65,535 after calibration. So the value may actually be 60,000. That is saturation for your calibration, because you're just subtracting off the dark current. So you certainly want to stay under that, and the more flux you have, the better off you are, because your noise goes down. So it's the square root of the signal is your noise. So you're better off keeping the noise down. So I'd say there's no standard value. So
Thank you. Alan Sanders says, thank you. It was great. Anybody, any additional questions or comments?
yeah, if anybody has any questions or additional comments on things, my email is listed at the bottom of this slide that's up here now. So you're certainly welcome to email me if you have any afterthoughts or questions. I'm no problem with responding and answering your questions. So I certainly appreciate everybody that was able to hang on for this period of time. It looks like we took up an hour and a half, which is quite a while to take out of your busy days, especially if you're in the office juggling things, answering phone calls and doing meetings. And it's certainly an awful lot of time if you're in the hot tub. And for those that wanted this as a motivation for a sleep age, it's time to wake up. So with that, I thank you for participating. So yeah, George, wake up.
Great. Hey, I got a good nap, Jim. I appreciate that.
All right,
That was,
good.
awesome.
Good.
No, we
Happy
really
for you.
enjoyed it. Thank you.
Okay, a couple of things before we go. There will be a short survey coming out asking about future topics for Ghostrock's Meet the SME. We would ask that you please take the time and fill it out so we know what you want to hear. Mike Hamill, I may have already read this. He said, thanks for the excellent presentation. John Webster would like to know, where can we get a copy of the video to rewatch what we missed?
Yeah, I don't think you recorded this, did you?
Yes.
Oh, you did. Okay. All right. Well,
It's
they're
sort
certainly
of,
welcome to email me, and I could forward slides if they wanted.
So the real Karen Brewer said that this will be posted and that information will be available. And Brett Mulhauser said, thanks, Jim. Great job.
Oh, good. Well, good. Again, I want to thank everybody. So
Thank you all very much. It's been a
All right.
pleasure to facilitate this session. Enjoy your
All right.
day.
thanks, Barbara. Thanks, George.
All right. See everybody later.